Thanks everyone for attending my talk. I'm Mohamad Mokbel, and today I'll be talking about exploring JARM and active TLS fingerprinting algorithm. First, this is not my first time in Amsterdam. I think this is my third or fourth time. What a beautiful city. I come from Toronto, Canada. Cheers. And as a small riddle, just take it as an exercise till the end of the talk. Can you figure out what does JARM stands for? Okay. It is an acronym, just as a hint. So a bit about me. I'm a senior security researcher with Trend Micro. I work for a digital vaccine lab where we analyze malware, vulnerabilities, and whatnot. So we have our own hardware intrusion prevention system. My interest lies in the area of reverse engineering, malware research, intrusion detection, and prevention system. And I have a special interest in C++ in particular, and compiler optimizations. And I'm a fan of exotic communication protocols, be it over whatever underlying channel. So since the talk is about TLS SSL, it goes without saying that we should introduce the TLS SSL handshake part. So when you establish a TCP connection, first you got the three-way TCP handshake, since enact the connections. And then you've got the TLS SSL handshake. That is, it starts by sending a client TCP handshake message. It's a packet, and the server acknowledges the packet. And then it follows by the server sending the TLS server hello packet. So these are specially crafted packets, be it by the client, your browser, and the server acknowledging what's in the packet to accept it. And it's important to note that these packets, they are not encrypted for any version of the TLS SSL protocol. What this allows us to do is that we can inspect these packets and we can post-process them off of PCAP or a binary file. So how does a client hello packet looks like at the TCP dump or Wireshark level, in case you're curious? So this is how a packets look like. So first, you've got the, it's telling you that it's transport layer security. The record layer handshake protocol is the client hello. So keep note of that for later on. And each of these fields has their own representation at the hex level. So the content type, it's telling this is the handshake message of client hello type. The version the client is using is TLS 1.2. And as you can see, it is represented as a word type value, 03 for the major version and 03 for the minor version. And the length of the next payload is 419 bytes. So again, the handshake protocol is a client hello type. And then you've got the version, you've got the random 32 byte nonce. Then the session ID, which is random as well. And the list of cipher suite that the client is advertising to the server, that this is the list of cipher suite that can accept. And it's up to the server to choose one of them. Okay. So in this case, it's 69 suites. Of course, you can have more. And then the compression method that the client is willing to negotiate. And then, of course, you've got a list of extensions. And the extension is not specific just to the ones I'm listing. You have way more. And in particular, like those that are used by JARM, they are specific to this list of extensions. The server name goes without saying. It is the server name that you're contacting. And the extended master secret key for the negotiating the key with the server. And they've got the max fragment length, renegotiation info, supported groups, and the elliptic curve point formats, the session ticket, and the application layer protocol negotiation. And then we'll go into some of these in depth later on. And then you've got the signature algorithm that your client is willing to support, the key share, and the PSK key exchange models, and the supported versions extension, which contains a list of TLS versions that the client is willing to accept. So this is how it looks like in a nutshell. Again, the client is advertising to the server that this is what I have, or I'm willing to accept. Pick whatever you want. So on the server side, the server will respond, okay, I got it. I will speak to you with TLS version 1.2. And this is my random value. And this is the cipher suite that I picked from the list you gave me. and not the word value 0xC02B. So this is the hex value for this cipher suite, which contains the authentication, the hashing, and the encryption algorithm. And you've got the list of extensions that the server accepted. So now we talk about JARM. But before we talk about JARM, we'll talk about GA3 and GA3C, which are both presented by Salesforce. These are prior to introducing JARM. So GA3 is a passive fingerprinting algorithm, and it works by passively parsing the TLS version from the client hello message, the ciphers, the list of ciphers, not the string representation, the word value representation for each of the ciphers, and the extensions, by the extension meaning the extension type, which is also of word value. And then the elliptic curves extension and the elliptic curve point formats. Okay. And then the way it works is you get the word values for each of those attributes. And then you convert them to decimal. And then you delimit them with a comma. And then for each of the attributes, if they have more than one value, for example, the extensions attribute, you separate them with a delimiter, a dash. And then you MD5 hash the whole thing, and then you get a hash for the GA3 algorithm. And the same thing goes for the GA3S, which is for the server hello message. You parse the TLS version, the cipher, and the extensions, and you do the same thing, MD5 hash the thing, and you get a fingerprint. That's called GA3S and GA3. However, if you've read the literature, you will notice that this is very prone to false positive. And we even did our own implementation for assessment, whether to integrate in our own IDS or not. It is very prone to false positive. Considering what it's accounting for, they are not enough to withstand or to be specific to a particular client or server. You'll see later on why. Now, going back to JARM, JARM is different from GA3. GA3 is passive. JARM is an active fingerprinting algorithm, meaning you construct a 10... I guess I need to use this. Okay. So JARM works by sending specially crafted 10 TLS client hello requests. And each of the requests contains different options. And it's meant to interrogate the server, see how it responds to each of those client hello requests. So if you send something valid, invalid, you change the order of the parameters, how would the server react to these changes? So the stuff that it sends to the server includes list of ciphers, TLS and TLS minor version, and list of extensions. Sorry, I meant by this, this is what what you get from the server hello message. So after you send those 10 specially crafted TLS client hello message, out of each of those requests, you parse the server hello packet looking for the cipher that it picked, the TLS minor version, and the list of extensions. So after you get all of this data from the server for each of those 10 packets, you parse them, you fuzzy hash them, and then for the extensions alone, you SHA-256 hash it. And you take only the first 32 characters out of it. And finally, you concatenate both the fuzzy hash for the cipher TLS minor version and then the SHA-256 for the list of extensions. And that gives you, in a nutshell, the JARM 62-character fingerprint. This is at a very high level. Now we'll go into the details later. Now for the talk layout, the motivation. So why am I doing this work? I mean, I'm not the guy who came up with JARM. So why am I talking about it again? First, as you'll see later, all of the implementation of JARM is in Python and Go, and there was no C++ implementation. I was curious about how the algorithm itself works internally, since there is no publications about the dynamics of the algorithm. They just did the implementation, and they did some scanning on the internet, and they gave us the results. But there's no actual work about how it works and how each of the packets are constructed. So I was curious about doing that myself. So I implemented it in C++ to see how it works. And I have another threat hunting framework that I wanted to use it as well for, which is written in C++. So I couldn't use Python or Go. Prior work, sorry, we'll talk about what others have done with this algorithm, and then the types of requests, what each of those requests represent, and the JARM-Raw Fingerprint, which I call like it's an intermediate representation before you get the final hash, and the hybrid fuzzy hashing part of the algorithm, which includes just the cipher suite and the version, and then some examples and interesting fingerprints. And of course, how to decode, demangle a JARM hash. Like after you get the hash, can you reverse some of this final hash back to its original state? Especially the fuzzy hash part, not the symmetric part, the list of extensions. And why ironities includes some of the anomalies when you get the hash, like how the server reacts to sending these 10 specially crafted client hello mesh. Sometimes they accept some of the mesh, sometimes they don't, like in a very short period of time. Why do they do that? And the demoing the tool, how it works. So prior work, of course, first you've got Salesforce. Back in November 2022, they introduced this algorithm to the public, and this is their blog. And their implementation is in Python. And then after they announced it, a lot of vendors start using it, including VirusTotal, Shodan, Binary Edge, Census, GitHub users, and many other GitHub users that have their own implementation, or even sharing some of the hashes publicly for malicious purpose, or not malicious purposes, like identifying malicious servers that communicates over TLS, like for malware and whatnot. And then you've got a JARM randomizer. JARM randomizer, actually, this work is presented by Dagmawi Mulugeta. This actually was presented here at HITB ComSec track in 2021. And this is meant to evade JARM-based detection by proxying the request before it reaches the server. That was a good work. And then you've got PyJARM implementation by Palo Alto Network. This is Python implementation, but in a library format that you can use in your own product. And of course, you've got the HDMore, the famous HDMore Go implementation for JARM. And then the best use case I found for JARM is by this guy call himself Sketchy Moose. And he has a tool called Works Like a JARM. It's very simple. It's probably about 100 lines or 150 lines of Python code, but it's dependent on VirusTotal API. So you would have to have like a subscription-based API. But it proves its worth in the sense that, so the idea behind it is you send a request to VirusTotal, looking for a search engine optimization-based poisoned results for some of the domains. So you say, I'm looking for example, AnyDesk type domains that are impersonating the official AnyDesk domain. Okay. You give just this list of keys, like in an array. And then you said to VirusTotal, I'm looking for a newly created domain off of this date. Let's say 2023 starting February. All the newly created domain after this date, get me those domains that contains this keyword. For example, AnyDesk on them, right? Then after you find this list, get me the JARM hash of all of these domains. Then off of this list, by that I mean the JARM hashes that you got, find me matching domains that have the same JARM hash, because they are meant to be like part of the same campaign that are imitating those legitimate domains. And even I tested the tool myself, and it works perfectly, actually. Why? Because of the constraints that the author put, being the creation date of the domain or whatnot. So you end up with a less false positives. Now we talk about JARM itself. The TLS client hello packet types. So you've got 10 requests. Each of those requests are specially crafted. And the names for each of those requests, actually, I'm borrowing from the original implementation, from 1 to 10. But what each of those requests represent, like what does it mean when you have forward, keyword, reverse, top half, bottom half, or whatnot, okay? So for example, For the forward request, you've got the 69 cipher suites in the request, in the client hello request that you're advertising to the server. And they are listed in specific order. And they are ordered such that from strongest to weakest. Okay, and then you see how the server will react to this request. Which one it would pick if I have the cipher suite list ordered from strongest to weakest. Then the reversed, it is the reverse for the cipher suite. The cipher suite list is ordered from weakest to strongest. In your mind, why the server should mind the order of the cipher suite if it knows what should pick, whether it is strong, insecure, or weak? But apparently it's not the case. The order does change the mind of the server response. So the top half, it's also about the cipher suite ordering, such that the first 35 changes the order, not the last 35. Sorry, not the rest of the 69. And the bottom half is to change the 34 out of the 69 cipher suite lists. Again, the order is from strongest to weakest. Now for the middle out, here is you introduce degrees word values in the cipher suite. So the degrees extension, which is proposed, I believe, by Google, it's meant to check for compatibility or incompatibility, I should say, depends how you look at it, on the server side. So these are, you should think of them as reserved values that the server should never pick up. So if I send you these values anywhere in the extensions, you should never pick up these values because these are reserved by the standard, TLS standard. And they have special format. For example, the first nibble between 0 and F, and the second nibble is always A, and it's always of 2 bytes value. Okay? So you're just interrogating the server for any anomalies. Now, and of course, it goes without saying that each of these packets are the TLS 1.2. It's telling the server, this is the version I'm using to communicate with you. And as you can tell, as you go down the list, this version changes from 1.2 to 1.1, 1.3, and so on. Now for the reverse, for packet number 8, it is the reverse order of packet number 7. So packet number 7, it is from strongest to weakest. Number 8, it is from weakest to strongest. However, for 7 and 8, they include the ALPN extension, which we'll get to it later. Now, invalid. Why would you send an invalid request to the server? And how would the server react if I send it an invalid request? I mean, of course, invalid meaning does not adhere to some of the standards elements. So what's invalid about this request, you might wonder? So as you construct this invalid packet, the invalid part is, so in the TLS record version, I have 1.0 version. But in the handshake version, I say 1.2. So let's see what version the server will pick, or how it will react to it, since there's inconsistency in the request I'm sending to it. So you can see where this is going now. Now we'll go to the raw fingerprint, how it looks like in JARM. So for the raw fingerprint, as you're parsing the server response, that they're sending those 10 specially crafted TLS client hello messages, you're going to look at the server response, parse the cipher suite that it picked, the TLS version, the ALPN extension, and the rest of the extensions. By the rest of the extensions, I mean the type of the extension, not what the extension includes. You don't care about that, about the value. And keep in mind that all of these that are encoded in TLV format, like you've got the type, length, value, so you know how to parse them at the binary level. So for the cipher suite, as I mentioned, it's 16-bit. And the way you delimit all of these values after you parse them with the server is with a pipe delimiter. And we'll see later on, like in case there is no value, what do you put instead of like an empty value? In this case, it's 00 for cipher suite. The same thing goes for TLS version. And the LPN extension, keep it empty. Okay. So I think now it's time to talk about ALPN. ALPN is Application Layer Protocol Negotiation Extension. You're advertising if this is like for performance reasons, introduced for performance reasons, technically speaking. You're advertising to the server the underlying protocol that you're willing to support on top of TLS. An underlying TLS. By that, for example, HTTP 0.9, 1.1, 2.0, 1.0, what else? Quick version. And again, keep in mind the way like these 10 requests, they also change the orders of the values within the ALPN extension and see if the server changes its mind based on the order of these values. So let's say I send a request to google.com to get the JARM hash off of it. And this is what gives me this 62-character JARM hash. All right. So of course, you have first the colored version, which is the first 30 bytes. And the rest is, as I mentioned earlier, is the SHA, the first 32 characters of the SHA-256 hash of the list of extensions that you get from the server. Again, keep in mind the extension is the extension type only. So this is like the intermediate representation of what you get from the server for each of those requests. Like you don't get this in JARM. JARM is just that. But this is the intermediate representation. So the C02B is the cipher suite type that the server picked from the list that I sent it out of those 69. Okay. And this is documented in the standard. And then you see it's delimited by pipe. And then you've got the 0303, which stands for the TLS minor version, major version. First one is major version. And the next byte is minor version. And remember, the representation for those is, although they are hex bytes, but the way you exercise them is at the text level. You treat them as strings. Okay. And then what follows after that the H2 in this case, this is for the value that picked from the ALPN extension out of all the value that I sent. And then what follows after that, the types of each of the extensions that the server responded with. And since we have more than one value, you delimit them with the dash character. It's clear, right? And the same thing goes for the rest of the requests. Now, of course, you can see here that Google did not accept the invalid request because it's all empties for all of the fields, which is good. Now, you might be wondering, so C02B, how come like you end up with 27D and these values? Like, how do you go from this to that thing, right? So at the implementation level for the cipher suites, you have an array. You build an array of these 69 values in the specific order mentioned by the original implementation. Okay. So you get the index of that cipher suite in the array. So for this one, for example, C02B, it happened to be at index 27, starting from 1, not 0, right? So that's how come you end up with 27 in the JARM hash, in the fuzzy hashing part. Now, the D, what does the D represent? So it's again the same thing. D it's an encoding for the minor version of the TLS version that the server responded with. We'll see later how. And the story repeats for the rest of the 30 characters in the fuzzy hashing part. So for every request, you get 3 characters for the first 30 characters. So no wonder you have 30 characters part of the fuzzy hashing part, since you've got 10 requests. So, and this final line here shows how to do the extension part. As you can see here, so you've got the ALPN extension, and then, of course, you get rid of the pipe delimiter, and then you add the rest of the extension types, and you do it the same thing for the rest of the requests, and then you SHA-256 hash the whole thing as string, not hex, and then you get that value over there. Only the first 32 characters, only the first 32 characters of the SHA-256 hash. Now, for the fuzzy hashing part, remember those 27 Ds, the first 30 characters? Like this is how I implement it, okay? And it's not much different from the original implementation. So first, you get the cipher bytes, okay? By that I mean the type And then let's say the server responded with nothing. You return 0, 0. You have to represent it with something. It's not valid. So remember, the cipher suite starts with the index 1, not 0. So 0 here doesn't mean index 0 in the cipher array. 0, 0 means the server didn't return with anything. Okay. And the cipher suite vector holds the type of the entire 69 cipher suite types. Okay. And in specific order. As you can see here, it starts with 0004 and 1305 and so on. Now you check for this cipher suite that the server responded with anywhere, if it exists anywhere in the array, and then you get the index of it. That's it. If it doesn't, then you return 0, 0. As simple as that. It's very simple. But that's the gist of it. Now, for the version, how do you parse the version that the server returned with? Like what TLS version it's going to be communicating with. Again, you get the version, the major and the minor. And if it responded with nothing, your return is 0. Remember that it is just one character for the version and 2 characters for the cipher suite. Because for the version, you have less than 10 possibilities. So this makes sense. So how do you encode the version? Since you saw there D, where does this D coming from? So the author chose to encode them via this list of options, A, B, C, D, E, F. He could have chosen any other characters, but this makes sense since they are hex all. And then the count variable is just getting the integer representation of the TLS minor version. I mean, this is just language specific stuff. It's nuance. And here it's saying if the count is greater than 6, return 0. You'll see later why. And then you check for that value, 0.3 in this case, the minor version is 0.3, right? That's the index. So that would be the index. Where would that fall? 0.3, 0, 1, 2, 3. So that would be D. You pick D out of it. You're just encoding the TLS minor version off of this list. That's all there is to it. Clear, right? So that's all it's doing. This is why, and this is, now you can tell why this is reversible. Like the first 30 characters. Now, the important part, so this is what each of those options maps to when you look at the final hash. So if you see at every third character in the first 30 characters in the JARM fingerprint, this is what you should be looking at from A to F. So if you see A, this means the server is going to be communicating with you over SSL version 3, right? So A, you see the index 0, 0, it's A. For B, TLS version 1. For C, TLS version 1.1, all the way to E, TLS version 1.3. So what happens if the server responded with F? Does it make sense to you? Of course not. Have you ever heard of TLS version 1.4? I haven't. So in case you see something like this, should freak out or should let everybody knows about it, right? That this server is either wrong or something wrong is in the implementation, or at least it's interesting to investigate further, right? So I'm pretty sure this, like the author put the F is for future versions, but since we're not in the future yet, so this is enough to flag any request with this value as worthy of further investigation. Now we go into some of the hashes. Okay. Now you might be wondering, why do I even have to have a JARM fingerprint for fingerprinting TLS SSL servers? So for malware, they use different communication protocols. Some of them over plain text, such as HITB, custom TCP, custom UDP protocols, or whatnot. Some of them, they are just plain text. You can detect them with a snort tool. So sometimes, like deep in the TCP flags, they would be communicating like tunneling some value in the TCP flags or something like this, right? This is easy to write filter for. And even if they are communicating over TLS, but not 1.3, they would be using a certificate. So the server would have to respond with the certificate which contains the public key. And a lot of them, they use self-signed certificates containing unique attributes that makes it easier to identify them. Although the traffic is encrypted, but you could still identify them at the certificate level. Now, if they are using TLS version 1.3, the certificate part is encrypted. So you're left with pretty much nothing unless you want to use some fancy machine learning technique or whatnot. So this is why JARM seems to prove itself in this specific case. So this slide contains some of the JARM hashes for some of the famous malware families. Okay, and the last column contains some of the matches against some of the services. Then you see the possibility for false positive or not. For example, for the first one, Trickbot, when I scanned it against top 100,000 WordPress sites and top 1 million Alexa website, I got 0 hits on it, which is good. It means I can fingerprint Trickbot servers with high confidence. And the same thing goes for Asyncret and Metasploit and Cobalt Strike. However, for Metasploit, if you search on VirusTotal with the domain entity, you get 1,000 hits for this specific JARM fingerprint. Are they all benign? Some of them malicious? You would have to do further investigation. And if you do the same search, but with the IP entity, again on VirusTotal, you get 1,200 hits. For Cobalt Strike, funny enough, you get 0 hits on WordPress and Alexa. But if you search for VirusTotal with the domain entity, you get 277,000 hits. What are the likelihood that all of these 277,000s, they are Cobalt Strike servers on VirusTotal? I don't know. This is definitely, there is a room for investigation here, meaning they could be false positive. So, which means Cobalt Strike has VirusTotal has a good database for actual presentation of what's happening with these hashes. So again, if you search by the IP entity, you get 4,400 hits against this hash. Now for Merlin, Merlin is an open source red team between Double Code framework. You got 3 matches on WordPress, meaning it's matching against legitimate servers too. And 303 matches against Alexa top 1 million. I mean, that's still relatively good, but not on VirusTotal. So VirusTotal gives you for 50,000 matches against this hash. I don't think there is that many Merlin servers active in the wild, like for 50,000. I don't think so. So this is an indication that most of these are false positive. And if you search for the same hash on Shodan, you get 10,076 matches. So we saw how the hash looked like and some of the examples in the wild. So let us say you get a hash from somebody and you want to investigate it. In this case, you get this Trickbot hash. What makes it unique, right? Why is it that we couldn't find any false positive against it out of the top Alexa and top 100,000 WordPress sites, not even on VirusTotal, other than Trickbot matches and whatnot, right? What makes it so unique? If you remember, first thing that should click in your mind, the first 30 characters, look how they all are repeating except for the third packet, 09B, right? But what stands out here? Can anyone tell me what stands out? Number 3? You mean the third packet? What else? Number 9. Exact. Why? Exact. It's invalid, right? In the record, I am advertising a TLS version, and in the handshake, another TLS version. It looks like the server didn't care. So it accepted the invalid request with the same cipher suite, which is interesting. And look how the server, despite in each of those packets, I'm advertising like more stronger version of TLS. I'm telling the server, I'm willing to accept 1.3. And yet for all of them, it picked version 1.0 for TLS. Looks like it's set. This is it. This is what I'm willing to do. No matter what you give me, this is all I'm going to accept from you. Okay. So this is actually what makes it unique. And in particular, the 9 packet and the fact that it responded with the same cipher suite, irrespective of the O-ring and the ALPN extension, the degrees that I mentioned, all of this stuff, it just stayed put to all of these values, except for a pack 3, which is interesting. Why the server changed its mind to choose another cipher suite? God knows. And the extension goes without saying. It doesn't change anything in this case. So let us look at something that's not unique in terms of false positive or being shared with other servers. So we take this hash as an example, right? So this particular hash, it's from WordPress, one of our WordPress sites. But the same hash is shared by 19,292 servers out of 9,055 WordPress sites. Okay? Sorry, here I should say 90,000. Okay? The 0 is missing. Otherwise it wouldn't make sense. So at the time when I did the scanning, 90,000 was active out of 100,000 WordPress sites. But you get 0 hits on Shodan. Now you might be wondering, how come 19,000 out of 90,000 servers have the same hash? If you look into, investigate some of those servers, you will notice that they are front end for Cloudflare. They are just acting as proxy. So no wonder they would have the same hash. And then this goes back to the prior work about the proxy randomizer. I'm not saying that proxy randomizer is at play here. I'm just saying that it's Cloudflare, all of them using Cloudflare. So no wonder you get the same hash. And thereby making it, how to say it, non-unique in terms of identifying the actual server, since you'll be identifying the proxy in front of your server. Okay? So what makes this interesting is another thing to keep in mind if you look deeper into the cipher suite is in packet 2. Actually, the tool gives you this information. And none of the other public tool gives you this information like this. Okay? So here, for the cipher suite 0xCC14, this is actually unassigned by IANA. It was assigned previously, but then they deprecated it and they introduced another value for the same cipher suite. So this is old. It's not used anymore. Yet the server, there's an equal cipher suite for this specific cipher suite. So you should pick the new one, not the old one. Okay. But this server picked the old one. Okay. Which is funny. I mean, it's still recommended in terms of security. So R stands for recommended. Okay. And in packet number 6, you can see that the server picked the cipher suite that's weak. That's weak. So you see here, I have it highlighted with the W at the end of it, like the postfix. And the R stands for recommended. But what's interesting again is for packet number 4, the server didn't accept this request. Why? I don't know why. And this, of course, number 9 goes without saying. And as you can see over at the end for the versions, it sort of maintains some consistency in terms of the TLS version it picked, 1.2, which is good, except for the weak part, version 6. Here, actually, if you want to be really more strict and more verbose, what you can do, some of those cipher suite types or values, sorry, I should say, they fall under specific TLS versions. So you can go even further by pinpointing some discrepancies in terms of what each of those TLS versions are picking. What if they are picking a cipher suite value that does not belong to a particular TLS version, right? So you can go that far. Again, more on JARM fingerprinting. It is for the xdadevelopers.com server. And here I'm just illustrating how the minor version works, the 0.3 part. Okay. Notice here, for example, I'm sending TLS 1.1, the server, just 0.2, just some illustration. And here again, for another server on Trojan, just notice how this hash, like the commonality of this hash on Trojan, you've got 11,000 matches, and this is again, I don't know, this is the same as, similar to the previous one. It's a front-end server for Cloud Front 2. This is checked as of May 31, 2022. Again, look how the server didn't accept packet 3. There's actually nothing unique about packet 3 in terms of the server rejecting it. But just the ordering, it seems to be changing the server's mind for whatever reason. Now we do some statistical analysis on, like, when scanning the top 1 million websites. This list is from Alexa. Out of those 1 million websites, you get actually only 5,000 unique. That's not a lot of uniqueness out of 1 million, right? So that just gives you an idea that this fingerprinting algorithm is, if you don't know how to use it or in what context, it's extremely prone to false positive between double codes, what false positive represents in this case. For example, if you take first hash, it is shared by 138,000 servers. It's for the same hash, okay? The second hash by 997. Of course, some of the hashes are unique. As you can tell, the third one, which is I have it highlighted, only 2 servers out of 1 million, which is good. And the same thing goes for the other 2, and the list goes on. So if we pick these 2 servers, which is the third hash, then you see how it looks like when you demangle the hash, okay? Now what is interesting about why it is 2 out of the million? Because the server did not accept the last packet, right? There's no value. Out of all the examples we went through, none of the server rejected the packet number 10, okay? And then this is actually pretty much like this graph is the same as the previous slides, but showing on a graphical representation. And as you can see, the concentration is like out of the 5,000 unique hashes, you can see that the concentration is, you remember that 138,000 hashes. So the concentration is at this, and it goes down. As you go down, like it goes to even less than 20,000 all the way to along the line. Of course, from 138,000, you drop gradually. You don't jump from 138,000 to 2 hits. But I don't mention those, but this graph should represent the slope of the uniqueness of each of those JARM hashes. Now, more on the statistical side, if you want to check for some insecure ciphers that some of those servers are using. So from the top 100,000 WordPress sites, you get this hash, and then you see it. It's using this insecure cipher suite. It's funny. I just want to play like with the tool and see what are some of the servers picking, because since it is relaying this information to you, so you might as well investigate it. And the same thing goes for this Europlayer side. It's using an insecure cipher suite. And for example, 55 domains from the top Alexa 1 million domain use this insecure cipher suite. Imagine they're still using RC4 encryption, right? It's insecure. It's not weak. It's insecure, meaning you shouldn't be using it. It's proved to be insecure, attackable. And the same thing goes, like another example for the another 149 domains from Alexa top 1 million uses this cipher too. Just changing the hash for the HMAG digestion from MD5 to SHA doesn't make it any secure. So, which is also insecure, like SHA by itself. The same thing goes for MD5. And in case you're curious, there is this site called ciphersuite.info that rates each of those ciphers from like insecure, weak, recommended, and whatnot, which is very handy. And more on the interesting fingerprints for this particular version. So 842 domains from Alexa picked version 1.0, coupled with weak ciphers. Another 47 domains from WordPress top 1000 used the same version with weak and insecure ciphers. And one domain in particular, like I highlighted this domain in particular because it used SSL version 3, not TLS, SSL version 3, which is interesting. Just one domain out of 100,000. And this domain actually seems to be famous. Like the category of this domain is business and economy. But I just found it funny that out of all of these, you got one that picked SSL, not TLS. And 2 domains from Alexa from 1 million picked SSL version 3. And coupled with weak and insecure ciphers, these are the domains. So JARM, but what does it mean exactly when you get this hash? What makes JARM fingerprinting unique or not unique? I think you should draw your own conclusion by now without me saying it. But since we are specially crafting these requests, it's different from what an actual client would send to the server. And there's a lot of factors at play that would change the hash itself. So, for example, you have the library used, the version of the library, the OS version, the order, default settings, and configuration on the server side. Okay? So as you're interrogating the server with these 10 packets, the server would change some of the values based on these specifics. And as I mentioned earlier, like as we've seen, the TLS version itself, like what does the server support? What TLS version, right? And for example, will the server accept a TLS 1.2 and a TLS 1.3 request? Again, the order of ciphers, depending on the order which one the server will choose. And of course, my favorite, the ALPN extension and the Grease extension. And by looking at the JARM fingerprint, so what does it mean if the first 30 characters match, but not the last 32 characters? So it means that the configuration is similar, but they're not exactly the same. So the servers, they're not exactly the same, since the list of extension it's responding with is different. Oddities. This is interesting. As I was like scanning those servers and playing with the tools, like this particular server picked my curiosity, end.gr. Sometimes it returns the ALPN extension, and sometimes it doesn't. Like in a very short period of time, as you're sending these 10 requests, for why I just couldn't figure out why we would do that. And this changes the fidelity rate in the fingerprint itself, which means you can't take it for granted. There are a lot of other factors at play. Could it be a workload on the server? Well, I wasn't DDoSing the server or anything like that. But nonetheless, something to keep in mind. And for the same server, you could also have different hashes at different times. Funny enough, in some of the stuff that I was testing, I would get the hash now, fast forward 5 minutes later, I get another hash. What has changed between the two time frame? Like, not much has changed, except the time moved on. Of course, the demo part. Does it work? So we will try. Can you? Oh no. How do I share the my screen, not the slides? Oh, I have to exit the slides? Okay. Oh, awesome. Thanks. So this is the tool. All right. So let us say when I get the JARM fingerprint for hit.com. Okay. So JARM, gosh, domain, HITB.com. Of course, you can specify the port, timeout, and whatnot. And then it sends the request, whatnot. Oh, you get the hash. Okay, so this is the hash you get for HITB.com. Now let's see how it looks like after you demangle the hash. You use the I for inverse. Let's see what it gives us. So, looks like the server rejected packet number 6, packet number 9, and packet number 10. The good news is none of the ciphers it picked are insecure or weak, which is good. You can already tell that this is actually unique, this fingerprint, because the fact that the server rejected these 3 packets, I mean, as we have seen, we haven't seen any server rejecting those three packets. And look how the cipher changes per request. And funny enough, like, if you look just at the first 2 packets, why would the server change its mind in picking this cipher instead of the first cipher? These are the only things that changed. It's the ordering of the ciphers. I mean, some of the other stuff that you could do. You can have a list of files that you want to scan. It will scan all of this for you and save them in a CSV file. Set different timeout for each connection to each of those domains. And you can be verbose. You can do this. You can get the intermediate representation of the fingerprint. By that, I mean V, D, HITB.com. You get this. And then from this, you can concatenate them and get the final JARM fingerprint by using the option R, -R for the raw argument. So in case somebody hands you, like you can, technically speaking, what this means is if somebody hands you a PCAP and you don't want to parse the PCAP manually, you can literally get these values manually yourself, looking at some of those fields, construct it as it is, and give it to the tool, and it will give you the final hash. See? Some of the third-party libraries I used hash library for SHA-256, available on GitHub. And for the TCP socket communications, I used SFML. However, I do not recommend this library. I had issues. By issues, I mean when I was trying to connect a non-existent domain, domains that takes a lot of time to respond. The tool doesn't have a timeout to close the connection. I had to implement a thread that would monitor the connection to the server with the timeout value that you specify in the client, such that if this timeout value expires, then close that connection so that it doesn't go waiting indefinitely for the server to respond to you. Okay, so there are some shortcomings to this library. I don't recommend it. But since I'm stuck with it, I'm stuck with it. And for some of the color stuff in the console, I use Color Console. And for the parsing from the command line, I use this C++ library. Of course, you'll never be done with statistics. One last slide on statistics. And you get this list, JARM hashes. You've got, the last column indicates the occurrences of each of the hashes in WordPress and Trojan. So, for example, the same hash happens to exist in 19,000 websites for WordPress, and at the same time, you get 236,000 matches on Trojan. So the last one, you get only 2 hits on WordPress, But on Trojan, you get 2,600. Okay, so just take these hashes with a grain of salt. Don't take them for granted as some absolute truth about the configuration of the server, okay? Conclusion, I never give conclusion. Usually it is the audience should draw their own conclusion, see if they understand what I'm saying or not. Thank you, and if you have any question, please do ask. And by the way, what does JARM stands for? Who has it figured out? No? No clue? Well, it's just the initials of the authors who came up with this algorithm. That's all. The initials of their names, actually. It doesn't stand for anything unique at all. And that's it. Thank you.
Questions? I have a question.
Yes.
Did you do any analysis from the server point of view on why certain anomalies were happening? So you control the server, you control the tool, you detect an anomaly in a specific configuration and try to understand why the anomaly was happening. What is the, as you said, the thinking behind the web server or the whatever web server you're using or software that produce such of these inconsistencies, like rejecting a specific packet or changing the selection of a cipher based on the order. So why they happen? We understood that they happen, but can we have some hints about why?
Oh, well, the easiest answer would be, like for the server that you would have control of, not like some of the discrepancies that I don't have control of. So in the implementation, you would have the way you have the list of cipher suites ordered, the server would pick the first occurrence, like as part of the logic. That makes sense. But is it the right choice? It's not the right choice. Like this is just like a replay attack. If you think about it, you can't be this naive to allow such a thing, right? You should have a list of secure, insecure, and list of whitelist, list of deny list. But the server picks what is like the order things. This is what's doing. And that's why you see this discrepancy. But in the case, if you see Google, although I'm sending it, insecure stuff, it's not picking it. It's sticking to the recommended stuff. So you can see how each server, decides what to pick and what not.
Is it possible to try to understand what, given a server, what expected behavior you will receive? Like, I don't know, Nginx standard default configuration behaves in a known manner.
Exactly. With that hash, it will identify those default configurations. So you get that and you work off of that to improve on it. If you want other cipher suites picked for every request, then you have to change it accordingly on the server side.
Thank you.
No worries.
Anyone else? Thank you so much.
Thank you.